important part of distance and matrices course, and we have reached the third part, which is about the distance matrix. So we will consider now another matrix. So I will just remind you that we have covered the adjacency, the incidence matrix. So we have reached the distance matrix. It stores the distance obviously between the vertices rather than adjacencies or incidence with edges. So reminder that at this distance it means the shortest path. So we shall see that the distance matrix can be generated with an algorithm that makes use of the adjacency matrix. So instead of calculating all these, we can try to get it from the adjacency. So given a graph, so this is what about the distance matrix. So given a graph of order n, so we have n vertices, so we can define the distance matrix. It's n multiple n matrix, so in terms of the vertices, and we represent so the distance between two vertices vi and vj as the distance between vi and vj. So obviously the distance between the same vertices is equal to 0, and we have the distance function metric, so it means that the distance between vi vj is equal to distance between vj and vi, so it's time metric. So in other words, the ij is equal dji, so the distance matrix is also symmetric and the diagonal is equal to 0. However, the value of the distance are not 0 or 1, so it's not binary. So since it's symmetric, so the transpose of the distance matrix is equal to d, and the diagonal are all 0. So we need to write the distance matrix of the following graph. So I have d, I have v1, v2, v3, v4, v5, v6. So since it's symmetric, I will work on half of the value. So I have 0 on the diagonal. So I need to work on the other stuff. So what's the distance, the minimum distance between v1 and v2? So obviously it's equal to 1. What's the distance between v1 and v3? So I have 2. v1 and v4 it's equal to 1. v1 and v5 is equal to 1, and v1 and v6 is equal to 2. So from v2 to v3 is equal to 1. From v2 to v4, so it's equal to 2. And from v2 to v5 also it's 2, and here is 1. Then v3 v4 is equal to 1, v3 v5 also 1, v3 v6 is equal to 2. Let's see v5. So I have just v3 v4 v5 is 1, and v4 v6 1 2 3 1 2 3, so it's equal here to 3. v5 v6 1 2 3 1 2 3, so it's equal to 3. So and then I need just to do transpose, so I will rewrite this row 1 1 2 1 0. I have here 1 2 2 1. I have here 1 1 2 1 3 and 3, and this is the distance matrix. So how can we obtain d from a? So here we have a very important algorithm. So let's first denote the value of k as the sum between I. It means the diagonal is equal to 1 plus a plus a2 plus ak. So as you can notice that whenever we are doing that, so in some of these a's, the diagonal or the values in ij entry, it could be different than 0. However, this is a0 here, it's equal to I. So here we are sure that at the diagonal we have 1. So whenever we are doing the summation between all these, we are sure that at the diagonal there is no 0 because of the first term. So this observation, it has a very important observation, since if I can reach to find a row that contains no 0, it means that there's a link and that we can reach that vertex. So we have a theorem here that if a graph with a graph with vertex set and adjacency matrix A, so the eccentricity of each vertex is equal to the minimum value of k. So minimum value of k, so this is k, it depends which term, which exponent of the adjacency matrix we have used, such that the row I, has no zero entries. So we will see examples on how we can calculate the eccentricity of each vertex using this idea. So directly an example. So we have this graph. So this graph is composed of 4 vertices and 4 edges. So let's write its adjacency matrix. So I have v1, v2, v3, v4. So 0, v1, v2 is equal to 1, v1, v3 is equal to 1, and then I have 1, 0, so I will directly do the transpose, and then I have v2, v3, so it's equal to, so there's no adjacency, so because we are writing the adjacency matrix, and between v2 and v4 there is 1, I will directly retranspose this. So between v3 and v4 there's no, and obviously there is no here. So this is the A, and then I will start with S1. So S1 is equal I plus A of 1. It's equal to I. So I will add 1 to the diagonal directly. So it's equal 1, 1, 1, 1, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1. So I will look over all these rows. I will see that the first row is all values are different than 0, so I can say that the eccentricity of v1 is equal to 1. So I need to continue, so I will calculate s2, which is equal to I plus a plus a2. So this is I plus a. I just need to add to this matrix the a square. So I have already calculated a square, so you can try to do it by your own, and it will be equal to this matrix. So 0, 1, 1, 1, 1, 1, 1, 2. So the answer would be at the end 4, 3, 1, 2, 2, 3, 1, 1, 1, 1, 2, 1, and 2, 2, 1, 3. So as you can see, all these rows that doesn't contain zeros, so we can say that the eccentricity of v2 is equal to 2, the eccentricity of v3 is equal to 2, and the eccentricity of v3 equal to 2. Why is equal to 2? Because this is the term of the sum. So you can say that, okay, I can continue infinitely, and I can sometimes cannot reach a state where all the values are non-zero. So when does this happen? Obviously when the graph is disconnected, because if it's disconnected, it means there's no way to reach to reach this vertex from any other vertex. So no matter which vertex v will consider, there's always a vertex vj. For this, there's no vi vj walk of any length. So obviously an ak would be equal to 0 in all the time. So how can we know when we will stop? So we know that we can stop since we are considering distances. It means geodesic passes, and since we have n vertices, we know that at the end of n minus 1 iteration, I should be reached that. So if I calculate ak or a n minus 1, and if still in a n minus 1 there is zeros, it means, or the summation whenever we are reaching the state or k equal n minus 1, and if there's always 0, it means that the graph is disconnected. So we cannot calculate that, because if there's a connection, obviously we know that the shortest path between any two vertices cannot exceed n minus 1. So a graph on n vertices is connected if and only if s n minus 1 has no zero entries. So this is one of the theorems, so I will write it here. So a graph is on n vertices is connected if and only if, so we have if and only if s n minus 1 has no zero entries. So we are sure of that. We have also a deduction concerning the radius. So We shall restrict now our attention to connected graphs, obviously, because we are not interested in disconnected graphs where distances are all finite. So we can also calculate the radius from the same rule. So for any connected graph, the radius of a graph obviously is the minimum k, such that at least one of the rows has no zero entry. So obviously it's the minimum eccentricity. So whenever we have calculated this, so at S1 we have calculated the eccentricity of the first vertex. So obviously the radius is equal to 1. So to determine the center, so we evaluate the running matrix sum. So we calculate S1, S2, S3, and so on, and stop as soon as we reach the smaller of the number k, such that Sk has at least one row with no zero entries, or we reach m is equal n minus 1, obviously. So in this case, the center is just V1, because at S1 I have reached to identify the first row that contains no zero. So, and to calculate the diameter, so it's the maximum eccentricity where all the eccentricity were calculated. So for example here the diameter would be equal to 2, and the periphery it contains V2, V3 and V4. So this is the center, so we have talked about that. So if the graph is connected, so the diameter is the minimum k, such as k has no entry, and obviously if it's disconnected, and if we do, for example, here Sn minus 1 iteration, obviously the diameter would be equal to infinite, and in our case the diameter would be equal to 2. So this is about how to obtain some of the value of the distance matrix from the adjacency matrix. So we move about the distance matrix realizability. So the question here is, whenever I gave you a distance matrix, does it represent a graph? Is it possible that it represents a graph? So an interesting but it's more difficult obviously problem is so given a symmetric matrix D of non-negative integers with all zeros on the diagonal, is D is the distance matrix of some graph. So obviously in order to say yes or no, I need to verify all the triangle inequalities. So that is that the distance between Vi Vj would be equal less than the distance between Vi Vk plus the distance between Vk and Vj, and this is for all the vertices in the graph. So let's take an example. So we will consider the following matrix to determine whether it is the distance matrix of some graph, and if so, find it. So we check that yes, here there's a diagonal and it's symmetric. So I need to verify all these combinations. So if we were to check the triangle inequality for all possible order triples, we would have to check. So here we have 6 multiple 5 multiple 4, because we need to, so we choose one vertex from 6, and then we choose a second one, and then we choose a third one. So it would be equal to 120. In fact, since it's symmetric, I can divide it by 2, and I need to do 16 verification. So this is too much, right? So usually we try to prove some inconsistencies in this distance matrices. However, you can try to see that it's right, it could be done. So how can we now draw the graph? So we first try to look of some recognizable subgraphs. So we already seen that we can look at some known subgraphs. So I can, for example, check, okay, I have here a very nice block. So it's equal to 0 on the diagonal, obviously, and on the other parts it's equal to 1. So we know that it means it's a K3 here, because it's all connected. So I know that the vertex of 4, 5, 6 are mutually adjacent, and they consider it's a cycle, it's a K3 here. And then, so I need to look to some other stuff. So obviously there's no blocks. So I need to identify how can I continue. So I'm sure here that V4, V5, and V6 are like this. So we try to link other vertices to this one. So obviously I may look at this row. So this row says that V3, because this is the row of V3, is adjacent to both V4 and V6, but at distance 2 from V5. So obviously I have a direct link from V3 to V4 and from V3 to V6, and directly I will have the distance 2 between these. So I have reached to place 4 vertices. Now I need to place also V1 and V2. So if I will consider V1 here, so as you can see, there are more ones in row 1 than row 2. Why? Because it's more easily to identify those vertices. So I know that V1, it's adjacent to both V3 and V6. So, and then I can verify all the other properties. I still didn't put V2, so this is good. Let's check if V1 is adjacent to V2. So the distance between V1 and V2 is equal to 2, so I didn't place it yet. So I have V1 and 1, 2, 3, V4, so it's equal to 2. Yes, it's equal to 2. So all the shortest path is equal to 2. V1 and V6 also is equal to 2. So I will calculate the shortest path. Yes, it's good. So obviously then I need to consider V2 because I need to place it. So I place V2 and try to link it. So V2 till V1, it will cost 2. So obviously I cannot link it directly. I can link it directly to V3. And if it's correct, I will have all these values verified. So this is the idea on how we can do that. So when the number of vertices is small and you are looking for a graph that realizes a given distance matrix, the problem can be solved in a reasonable time. So you can, so in our case, we have found here the best approach is building successively larger induced subgraphs in steps. So the distance matrix realizability, so usually it can be more difficult. And why it's more difficult, because in more complex problems we will see that those edges, they are weighted, so and then we will add weights to this graph, so it will be very difficult to this. Sometimes the weights are positive, sometimes the weights are negative, and it will be a very difficult problem to solve. So this is the distance matrix. So we'll move to our last part, which is about graph representation and implementation. So there are several ways to present the graphs in algorithms. So the choice of a structure or data structures depend on the size of the graph and the way the algorithm processes it. So we have 3 popular representations: the adjacency matrix, which we have already seen. We have the adjacency list and the edge list. So we will cover each one and implemented for unweighted graphs and also for weighted graphs. So we'll do that at the same time. So we'll consider this graph. So the graph is disconnected, it has 3 connected components. So the input of our program in all for these representation is 9 vertices and 7 edges. So we have 9 vertices and 7 edges, and then on each subsequent rows we will specify the edge. So the first edge is between 0 and 1, and then 1, 2, and so on. So, and this is the input of our program. So the first part is about adjacency matrix. So an adjacency matrix, as we have seen, indicates the edges that the graph contains. So we can efficiently check from an adjacency matrix if there's an edge between 2 nodes. So the matrix can be stored easily as a 2-dimensional array where n is the maximum size. So each value indicates whether the graph contains an edge, obviously, and if it does not contain an edge between these 2 vertices, it would be equal to 0. So otherwise, if the graph is weighted, it means there's weight on the edges. I can place instead 1, I can place the effective weight that is associated to each edge. So the drawback of the adjacency matrix representation is that adjacency matrix contains n square elements. So n square because you have n vertices and multiple n is n square, and usually most of these values are 0. So this is why this representation cannot be used if the graph is large. So we will start, so we'll write the first program. So just I'm showing you the output. So this is the input, and we need to write a program. So it needs to fill an adjacency matrix, and then it needs to print it on the screen. So I will read, I will fill. So whenever I have 0, 1, I will fill in the matrix 1, 0, 1, 1, and then I need to display it. So I can fill half of the matrix, or I can fill the full matrix. It depends on your technique. So we will write a C++ program. So as you know, we'll not be using vectors, so it's the same as in C. So we'll have a constant size. I have already wrote the printing function just to print it, but we need just to write the main functions where we need to fill and read the two-dimensional array. So I need a two-dimensional array, so we call it adjacency. So it's the maximum size, and we'll see what we need. So as the input, as I specified, so we need a number of vertices and a number of edges, and we need to scan them. So scanf %t %d, address of v, address of e, and then I need to read the matrix. So since we are doing a C program, so we need to initialize the values to 0. So if we are using C++ as vector, we can use a sign. However, here we need to loop 2 times in order to place zeros. So for I equal to 0, I less than. So now I know that the number of vertices is equal to v, so there's no need to loop over size. And then for j equal to 0, j less than v, j plus plus, so capital V. And I need to put in adjacency ij, I should put 0. And then I need to read, so I need to read e element, so I will loop on I. For I equal to 0, I less than e, because the next input are the edges. And I will do a scanf, so let me do that here. I will do a scanf for 2 values, so I need also 2 values. Let's call them a, b. So scanf %d, address of a, address of b, so those are the vertices, and I need to put in the adjacency of of ab, sorry, if ab, I should put 1, and also I should put in ba, because this is not directed, so I can do it directly here, is equal to 1. So this is it. I have read the input. I just need to call the function print. So print, it just take an array, the matrix, and it prints it. So it's printing using 2 nested loops. So I will print v just to check. So v here, it means vv, because v is just the dimension, and since it's square. So let's run. So we need to give the input. So I will do it manually, obviously. So the input is 97. So 97, 0, 1, 1, 2, 2, 3, 1, 3, 3, 4, 6, 7, and 6, 8, and I will have the adjacency matrix, the following adjacency matrix. So obviously it's symmetric and easy to code. So let's move to some other part. So next we have the adjacency list. So what does it mean, adjacency list? So in the adjacency list, each node, so each vertex in the graph, is assigned an adjacency list that contains of nodes to which there is a match from X. So an adjacency list are the most popular way to represent the graphs, and most algorithms can be efficiently implemented using them, and obviously we will use adjacency list from now on. So a convenient way to represent an adjacency list to declare an array of vectors. So vector of integers, because our vertices are integers, it's adjacency, and it's an array of vectors. So here the constant n, so it's chosen to store all the adjacency list in the list. So I will talk about it more, but let me just show you how it will be the output. So I have, for 0, I will have a vector. So for each vertex, I will have a vector. So this is a vector, this is a vector, and all these are vectors. I have an array of vectors, and so each vertex it has a vector of integers. Later on, we will have vector of pairs, for example, or triplets. Who knows? So if the graph is undirected like this, it can be stored in a similar way, but each edge is added in both directions. So if it's direct, this is here undirected, so I can find it here and here, as you can see. However, if it's directed, we'll see it later whenever we talk about directed graph, it will be added to one of these lists. If the graph is weighted, I can use pairs here. So I can I can have, instead of a vector of int adjacency, I can have a vector. I have a pair of integers. So what does it mean, a pair? It means the first one is the neighbor and the second element is the weight. So for example, we will do it in a while. So for example, if I have here 4, so within 6 I will have 7 with a weight 4, and I will have 8 with a weight 3. So I can associate also. So I will have a vector of pairs if the graph is weighted. So using adjacency list, so we can efficiently loop over these because we have iterators. We already know how to loop over elements in a vector. So we have the same input, so we'll keep with the same input. However, we need to find a way or to implement using vector. It's very easy, as you will see. So let's move to our program. So obviously, I will remove all of these since I will start from a clean input. So we need a vector, obviously. So we need a vector. So let me see if I have included vector. So I will include vector in my include part. So I need a vector. So our vector is an integer. It contains integer for now. So, and I will call it adjacency. And for example, I can declare it as size, but since we are dealing with C++, I will be more tricky here. So I will read V first, and then I will declare a vector as a V element. So this is not possible in C, but it's possible in C++. So scanf %g%d. I can do same also here, address of V, address of E. And now I can create an adjacency vertex, adjacency of adjacency list. So this is a V. Next, what should I do? I need to just read. So also I need to, a loop. So I need I need also two values a and b because I need to push them into the vector. So let me erase this print because we don't need it anymore. Okay, so I need to loop over the number of edges for I equal to 0, I less than e, I plus plus. I need to do scanf %d, sorry, address of a, address of b, and then I need to push back all these. So in the adjacency of a, I will push back b. And in the adjacency vector of b, I will add a because it's undirected. So it's undirected. So we have here int v, expression must be a constant. So it's a constant. Okay, so this is push back. And then I need just to print all these. So for I equal to 0, I less than v, I plus plus. I will do cout I space, and then I will loop over the vector. So I can use the auto. So for auto b colon adjacency of I, so I'm looping over the vector of I, and I will print a b. And of course, after this, after each line, I will print end line. So I can do cout end line, or I can do cout backslash n, or I can do printf backslash n, and so on. So let me just do debugging. So there were error here. So expression must be a constant. So we couldn't use that. So obviously, so let's use size. So I still have a problem. What's pushback is undefined, so it's not equal, it's dot. Obviously we are still in C, but we are using the pushback functions. So let's do a build. C out, not count, so it's correcting for us. One more time, start debugging. So obviously if it works, so we need to do the start debugging without, because the screen will disappear. So let's re-enter the same values. So we have 9 vertices and 7 edges. 0, 1, 1, 2, 2, 3, 1, 3, 3, 4, 6, 7, and 6, 8. So we have those, so 0, 1. Let me open the same slide here and see if we can check the difference. So 0, 1, 1, 0, 2, 3, 2, 1, 3, 3, 2, 1, 4, 4, 3, 6, 7, and so on. So we have reached using this simple code to represent the adjacency list of a graph. So it should have worked here, but maybe I'm using this compiler. Maybe another compiler, it will work. So an online compiler, it will work, obviously. So we have here an adjacency list of vectors. So we have an array of adjacency lists. So our lists are, each list is about a list of integers, a vector of integers, and I'm pushing those values to the end. So let's suppose that so I will move a bit to a later slide, so where we have, for example, here the adjacency list with weights. So what does it mean, a weight? It means our input, it will contain weights also. So there's a third variable. So how can we do that more quickly? So I just need also to read the weight. So I will have here %d, and I will have a weight. So I will declare here a weight, and I will push not just b, I will push a pair. So our vector, it's not just about integer, it's about a pair of integers. So if I want to write this, I will say here pair int, comma, and int. So, and whenever I'm pushing new values, I can do make pairs, but this is not the purpose. So we can do, for example, like this. The first one is B, and the second one is W. And obviously also for the end here, I can do A, W. So the first value is A, and the second value is W. And whenever I'm printing, so here, whenever I'm looping over the adjacency, so the adjacency here, it's not just B, so you know we have two values, first and second, so I can write B dot first and B dot second. So if I want to be more, so the output here is edge 1, 0, so this is the adjacency list. So I can write more like this with weights and stuff. So we can do that, why not? So at the first, I will write here, so let me do it using printf, it's more easily. So printf, I will write edge %d dash %d, and then I will have weight equal %d backslash n. So the first one is I, the second one is b dot first, and the second one is b dot second. Right, so let's run. So here we have to supply 3 values at each time. So even if we have 7 edges, so we have the weights associated. So 0, 1, 3, 1, 2, 2, 2, 3, 1, 1, 3, 4, 3, 4, 2, 6 7 3 and 6 8 4. So let us check the output here. So we have edge 1 0 or edge 0 1 is equal to 3, edge 1 0 3 2 4 and so on. So we have reached to do that with weights. So we could have already done this with the adjacency matrix, but I have removed the code. So we just need to, instead placing 1, I will read the value and then place it in the adjacency matrix. So the third one is the edge list. So let me just talk you about the edge list. So as it said, so it's about edges. So I will store the edges. I will output the edges. How we will do that? So the edge list contains all edges of the graph in some order. There's no need to be in order. So there's a convenient way, though this is a convenient way to represent a graph if the algorithm possesses all its edges and it's not needed to find edges that start at a given node. So it has a really restricted usage. So the edge list can be stored in a vector. So as we have done for now, for the weighted graph for the adjacency list, we can use a vector of pairs of integers. So each pair AB denotes an edge from A to B. So if the graph is weighted, I will use a triplet or a tuple. So we will do it now and see how we will do that. Also, since we have a tuple, we can also use a priority queue. So this is the example of the edge list that is not the output. If I were using a weighted edge list, it would be like this. So the weight 1 for 3 2. I will order the weights by order, and this is done using a priority queue if, for example, I need to do that. So let's start first by doing the edge list one. So obviously, if I will go to my program, it would be the same because I'll be using a pair of stuff, and instead of using and calling it array of pairs, it would be just an adjacency list, an edge list. So I will call it just edge. So it's a one vector, and this vector, it contains just a value. So if I will go back, so our edge list here is just one vector, and each vector contains a pair of integers. So let us do this. So it's just an edge. So it's directly, I will read AB. So there's no here W because those are just two values. And I will add to the edge, I will add edge B. And for each edge, I will add also, so it's not edge B, it's AB. I will add the edge AB and I will add the edge BA. Obviously to the same vector. So at the end I need to print, I just need to print, so I will loop over edge here and I will print edge dot first, edge dot second. So %d, backslash n, and b dot first, b dot second. So that this is it. So if I will, so the output should look like this. So I will remove the dash. So let's run. 9 7 0 1 1 2 2 3 1 3 3 4 6 7 and 6 8, and we will have the output. So we need to remove just here the count I because the out I, because we are displaying for each time the number, the vertex. So and also we don't need the for loop because we are looping over one vertex. So okay, we can remove this, and the output would be as it is required, So if I have a weighted graph and I want to calculate the edge list, so obviously I need to read. So the input would be like this. Where's the input? So this is the input. It has 3 values, and I need at the end to have this. So as I have told you, we can use triplets we can use a priority queue. So I will be doing it using a priority queue. So as you can, if you remember that when using priority queue, it will be ordered in descending order. So in order to order them in ascending order, I will push first the weight, the negative weight of these, and then whenever we are printing, I will print the negation of these. So we'll see this trick because it's very important whenever we are manipulating queues. So for that, I will be including queue in order to use priority queues. So I'll be using pairs. So I will keep that. So it's in a pair of integers, int and integer. So in this case, I will have not just one integers. I will have two integers. Why? Because I have the first edge, the second edge, and the weight. So I can have, since I'm using a priority queue, it should have the weight as the first value, and the second one would be a pair. So it's pair of integers. So as you can see, so we have it's priority queue here. We'll not use a vector, so priority priority queue. So the first one is the ID. So it's a pair, so it's ID and then the value. So the value here, it's a pair of two integers. So I will call it also an edge. So I'll be reading V and E. Okay, I will keep it here. I will loop over and I will do a scanf, and then I will add to the edge some value. So obviously in priority queue there's no pushback, there's push. I will write it once and then I will copy it. So I will do a pair. So here I will have first, I will need also the weight. So W, address of W. So I will add in the first pair minus W. So this is Y. And I will add the pair AB. So this is the edge and it's associated with its weight. So it's edge like this. And one more time, I will add BA. So I have added this, I have added the negation of the weight so that whenever I'm adding it to the priority queue, it will be sorted in ascending order. And then I need to loop over edge to priority queue. I can do that, or I can loop over 2 times the number of edges. So it depends on what do you want to do. So I can do as long as there's not empty. So let's do that because we didn't do that here. So while the edge dot empty, so as long as not empty, what I will do, I will get a pair from this. So what does it mean, a pair? So I will declare a pair of type int. So I will copy this, and pair of int. I will call it, for example, E, and it will be equal to edge dot top. Obviously, I will do directly edge.pop in order to remove the element from this priority queue. And then I need to print just the values of the pair. So it has 3 values. It has first, it has second, second.first, and second.second. So I will write weight first. It would be equal to what's called E dot first. So here I will write it directly. Second dot first and E dot second dot second. So this is the weight, and then we have the edge. It's percentage D dash percentage D, and I will add a backslash n. So this is the implementation. Let's run the program. I'm just looking for the input. So this is my input. So debug. So I have made a mistake since I need to display minus the weight because the weight is negative. So why does it have error? So we have a semicolon missed. So 97013122231 134 342 673 and 684. And yes, I have AND with this. So let's check the output. So I have weight 1, 3, 2, 1, 2, 3, and so on, and everything was good. So it's we have used a priority queue. So and it's sorted ascendingly. So we have enqueued the negation of the weight so that it will be negative, so -1, -2, so -1 is greater than -4, but we have displayed the negation of this number. And this is it for this part. So we have seen how we can implement graph, so using vectors, priority queues. It's very easy to do that. So most of our work will be dedicated to adjacency list, not adjacency matrix, and not adjacency list. So no edge list. So it's mostly about adjacency lists where we use vectors intensively and extensively. And this is it for this chapter. If you have any questions, do not hesitate to use the forum on Moodle and to practice, and see you in the next chapter.